Alright, today we're going to start talking about inverse functions. The definition of inverse is that a function g is the inverse of the function f if the composite function, so f of g of x, is equal to x for each x in the domain, and g of f of x is equal for x in each of the domain. So what an inverse function really is it's a reflection about the y equals x axis. So basically, if I have two graphs that, let me go ahead and draw in the y equals x line. They're mirror images of each other, okay, and they flip-flop over that y equals x line. So really what happens then is that their ordered pairs flip-flop around. Not every function has an inverse. If a horizontal line intersects the graph of f twice, then it's not one-to-one and therefore doesn't have an inverse. So if we want to know if something has an inverse or not, we're just going to do a horizontal line test. So something along these lines, this passes the horizontal line test, so it has an inverse, whereas something like this does not pass the horizontal line test, so it does not have an inverse. So one of the things we're going to talk about is monotonic, and a function is strictly monotonic if it is either increasing on its entire domain or decreasing on its entire domain. This function increases and decreases and increases, so it's not considered monotonic. However, something like this is considered monotonic because it's increasing the entire time. So the existence of an inverse, in order for an inverse to exist, there's two things that will take place. A function has an inverse function if and only if it's one-to-one, meaning it passes that horizontal line test. So if it passes the horizontal line test, then it has an inverse. And f is strictly monotonic on its entire domain, and therefore it's one-to-one and has an inverse. So either of those two things can happen. The guidelines for finding an inverse, basically this is a long way of basically describing everything that you're going to be doing. Really what you need to know is that you're going to interchange the x and y, and we're going to result in the other equation. I think it's much easier, rather than reading all these and going through the process, just to go ahead and talk about some problems. So on this first problem, we're supposed to show that f and g are inverse functions analytically. So if I go back to what an inverse function is, it says that the composite function is equal to x. So we're going to go ahead and find the composite function and show that it's equal to x. So I'm going to start with f of x, and I'm going to say f of g of x. So I'm going to say f of g, here's my g, and then what I can do is say that what that really means is I'm putting that whole part in for x. Now, I think this is the complicated way of doing this, and you can make a common denominator and go ahead and do that. I'm going to show you a much faster way to show that it's the inverse function. And basically what we're going to do is we're going to write this as y equals 1 over 1 plus x. And we're going to interchange the x and the y. So what I'm basically saying is don't do it this way. You can just interchange the x and the y. It makes things way easier. Then what we can do is cross multiply. And notice I get x plus xy equals 1. And now what I'm going to do is solve for y. So I get xy equals 1 minus x. And then I'll divide by x on both sides. And I get y equals 1 minus x over x. I have now shown that f and g are inverses of each other because I ended up with the original function. To show it graphically, go ahead and take out your graphing calculator. And what you will find on your graphing calculator is that you will end up with a graph for one of them that looks like this. And for the other one, it would look something along these lines here. Notice how if I folded along the y equals x axis, they would be inverse functions. Alright, continuing on with inverse functions, what I'm going to now ask you to do is use the graphing calculator to graph the function, and then the horizontal line test to determine whether the function is one-to-one on its entire domain and therefore has an inverse. So all we're going to do is use our graphing calculator and we're going to graph it. So you guys should pause this and go ahead and type it in your graphing calculator. Alright, after you've put that in your graphic calculator, you should end up with some sort of function that looks like this. Notice it does pass the horizontal line test. Therefore, it is one-to-one and has an inverse function. So I'll just write that. This is 1-to-1 and has an inverse. On this next one, again, we're going to use the graphing calculator, and we're going to determine if it passes the horizontal line test. So pause the video and type in the function. Okay, you should have ended up with your graphing calculator looking something along these lines. That was not a good drawing. You should have like a horizontal line like this. Now, if you look at this, this does not pass the horizontal line test. Okay, so it's not one-to-one. So there is no inverse. Okay, on this next problem, we're asked to find the inverse and then graph f and the f inverse on the same coordinate axis. So we'll start with those. So if I'm going to go ahead and find the inverse, I'm going to interchange my x and my y. So my y now becomes x and my x becomes y cubed. And then what I'll do is I'll solve for y. So I'll add 1 to both sides, and I get x plus 1 equals y cubed. And then I'll cube root both sides, so I end up with the answer of the cube root of x plus 1. So what I'm going to do is say, well, this is actually the f inverse, and I am going to go ahead and graph that on the same axis. So you guys can use your graphing calculator on that. You should end up with something that looks like this. And if you graph f itself, it should look something along these lines. Okay, my graphs are definitely not exact, okay? But what else we're supposed to do is describe the relationship between the graphs and state the domain and the range. Basically, the relationship between them are that they're inverses of each other, so the x and the y values are flip-flopped, and you can tell my graph is not perfect because really that should be coming up here and this should be coming up here because they should cross each other at the same point. And then the domain and the range. So the domain of f and f inverse is negative infinity to infinity. So if you look at this, all the x's are covered. So it starts way over here at negative infinity and travels to infinity, and so does f inverse. F inverse does, and so does f. So f is here, and f inverse is the blue one. Sorry for the confusion there. The last problem we're going to look at, it says use a graph to make a table of values. So I will do that. So this is going to be f. I'm going to make a table of values for that. So this first point is 4, 0. And the second point is 2, 2. And the third point is 0, 6. Now that you've created your f table, you can now create your f inverse table. So I'll do that right here. So I would have x and f inverse. All that happens is that the x and y flip-flop positions. So all I'm doing is flip-flopping the x and y. And that's what occurs in inverses. The x and the y flip-flop spots.